Now if you want, if you look at the, say, sphere, and look at the north and south pole, and there are actually infinitely many ways it can go. And it's not unique and so on. But when they are closed, then there is only one. Okay, and well, it comes from the uniqueness of solution of some differential. Now, well, how do you do this? Well, that's what variational calculus is all about. You parameterize these, so we fix the endpoints, right? So, and, well, you need to distinguish between these curves somehow. So we could assign, well, let's say this is gamma, say another parameter, s. So the parameter s would be, it's a one parameter family of paths. Okay, so we have one parameter family of trajectories of curves. So basically gamma s of t. So there are two parameters in general, right? So one is when you change t, it moves, well, it moves along given trajectory with fixed s. When you fix t and change s, then you move, you know, from one trajectory to another. So if you move both of them, you get a surface that they span with this point being fixed. Is that clear? So, okay, so you get this so that gamma s of A is Q1 and gamma s of B is Q2. So these are fixed points. Okay, but S is a parameter. Now, well, because the endpoints are fixed, when you compute the derivative, you look at the, what is Q dot? So it is gamma S dot. It's the time derivative. By the way, dot is always, say, dot always means d by dt. Just as a notation thing. The derivative with respect to S will be just defined differently. So you have this thing. Now, what are the values of this and the endpoints? Gamma S dot A is equal to what? Well, 0, because they are fixed. Okay? So once you set it all up, then you say, okay, if you consider such family of curve, then the action becomes not just a number, but becomes a function of that parameter s. You compute it along specific trajectory, parameterized by s. You get a number that depends on that s, and so therefore you get a function. Okay? So, and you want that function to have a minimum. What do? You compute the derivative, right? So what you want is, well, now there are two s's, right? So there is this action, and I hope you don't confuse this. I mean, this is capital S, that's the action, this little s is the parameter. Well, let's write to be. So this is just to indicate that it depends on the path, on the map. And so you want to say, okay, you want to set this to 0 with fixed endpoints, and then that condition, this is called stationary action. In other words, when you, well, it is one very specific curve on which the action will be minimal. Stationary means the same thing, that derivative is 0 or minimized if they are closed and so on. And so once you have this, then you will see that that gives us a system of ODEs, which are basically the Newton equation and Hamiltonian equations or whatever for these variables. Well, they have a name, they're called Lagrange-Euler equations. Well, let's derive these equations. well, you do this, and then you just need to differentiate this. Both of these depend on s, right? So we compute ds by, well, it's not really, well, usually it's called, let me just denote it as A for action, okay? So you don't really confuse it. So I'm going to compute this derivative and set it to 0. So that's an integral. It's an integral that depends on the parameter, right? And so these will depend on the parameter s, so I can differentiate it. So what do I get? Well, you need to use chain rule, right? So I want to compute derivative of L, the Lagrangian with respect to s. But L does not depend on s explicitly, it only depends on it implicitly through these functions, right? So the coordinates and the velocity. So you'll get dl by dqi times dqi by ds, right? And there is a sum. There is sum of I plus dl by dq dot I dq dot I by ds dt. Right? So, now look at this. Well, look at this term. You have d by ds, and then there is d by dt with q. This thing commute. So, you can write it as d by dt, d by ds, okay? So and that's what I'm going to do. I put here this is equal to d by dt, d by ds, qi, right? Then, well, there is this d by dt, and I'm integrating over dt. So I can integrate by parts. My idea is to take that derivative, integrate by parts, and bring that derivative on that term. When you do integrate by parts, what do you get? Well, you get, you change sign and this derivative acts on that. But in addition, you get off integral terms, right? So you get this product, this times this evaluated at the endpoints. So you get this evaluated at the endpoints. What is it? 0. That's why it doesn't appear. So that's why this is equal to, let me write dt here. Well, then there is sum. So I get dl dqi by ds minus because I integrate by part d by dt dl by dqi. So that derivative acts on that, and then this dqi by ds. Well, that term is the same as this. I'm going to pull it out. Okay, so that's what you get. So this derivative is equal to this. Now, we have this expression times that. And so I want this to be equal to 0. I want to pick those paths, the trajectories for which this is equal to 0, right? Independently on this. So this will be equal to 0 if this term is identical or equal to 0. Because this is arbitrary. This can be whatever you want it to be. So you want this to be equal to 0 for arbitrary function, for arbitrary derivative. This is a perturbation term. You could take one